Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 26th, 2026, about 5 days ago. It introduces a new framework called On-Policy Self-Distillation, or OPSD, which allows a single model to serve as both teacher and student to achieve 4 to 8 times better token efficiency than reinforcement learning methods like group relative policy optimization. The paper is titled Self-Distilled Reasoner on Policy Self-Distillation for Large Language Models. And, as we will see later, the implications for training efficient reasoning models are quite significant. So Figure 1 illustrates the entire on-policy self-distillation pipeline, which is clever because it uses a single large language model to play 2 distinct roles. Starting on the left, we take a sample containing a problem and its ground truth solution. In the center, the framework splits into 2 paths, creating a student policy that sees only the question, and a teacher policy that sees both the question and the correct answer. The student generates a response trajectory, which the teacher then evaluates using its privileged information. Finally, looking at the right, the learning objective minimizes the divergence between the two, effectively updating the student to match the teacher's hindsight reasoning. While Figure 1 outlines the mechanism, Table 1 compares this approach against existing methods to highlight the specific trade-offs. Looking at the group relative policy optimization column, we see it operates on policy but suffers from sparse signals and high sampling costs. Standard on-policy distillation solves those efficiency problems but introduces a dependency on an external teacher model. The final column demonstrates how on-policy self-distillation bridges these gaps, securing all 4 key advantages, including dense feedback and low compute costs, without needing a separate teacher. Alright, moving from the high-level comparison, Figure 2 shows exactly how the authors prompt the model to adopt these 2 different personas. The top section displays the student prompt, which mimics a standard test setting by providing only the problem statement without any extra help. The bottom section, however, reveals the teacher prompt, where the model receives the reference solution as privileged context. Notice the specific instruction in bold. It asks the teacher to first understand that solution and then rederive the answer, which ensures the guidance remains grounded in the model's own reasoning style. So, having seen the prompts, Table 2 presents the main performance results across 3 model scales. Looking first at the QN38B section, on-policy self-distillation achieves the highest average accuracy of 52.2%, outperforming both supervised fine-tuning and group relative policy optimization. This advantage persists in the 4B model block, where the method again leads with an average of 50.6%. However, at the smaller 1.7B scale, performance ties with the reinforcement learning baseline, suggesting self-distillation works best when the model has sufficient capacity. Well, while Table 2 established the scaling laws, Figure 4 investigates how the length of reasoning chains affects performance on the QN34B model. The graph plots pass at K accuracy against the number of generations, comparing different token limits. The 3 solid lines represent on-policy self-distillation, with budgets of roughly 1,000, 2,000, and 4,000 tokens. Notice that the light green line for 4,096 tokens sits at the very top, clearly outperforming the dashed orange line for group relative policy optimization. This confirms that longer generation budgets allow the student to receive richer, more comprehensive feedback from the teacher. So, Figure 4 examined trajectory length. Figure 3 highlights the critical advantage of token efficiency. The left panel plots accuracy against gradient steps, where the blue on-policy self-distillation line climbs faster than the orange group relative policy optimization baseline. However, the right panel reveals the real cost difference by tracking total tokens generated. Here, the blue line shoots up vertically, reaching peak performance with very minimal compute. In contrast, the orange line stretches far to the right, requiring significantly more samples to achieve similar results, which confirms the method is 4 to 8 times more efficient. Wrapping up, 2 takeaways stand out. On-policy self-distillation delivers massive efficiency gains, cutting token usage by 4 to 8 times compared to reinforcement learning baselines. It also simplifies the pipeline by letting models teach themselves using ground truth answers, eliminating the need for external teachers. This suggests high-quality post-training might not always require massive compute. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.